All right, guys, welcome to lesson 6.4. We're going to talk more about properties of integrals. I'm going to incorporate those same properties that we were looking at before, but just going to look at a different kind of question where we can use those sorts of properties today. So before we begin, though, let's review how to find the area of a circle. All right, a circle, as you know, has a radius. And the area of a circle, as you probably remember from other lessons in this class, is pi r squared. Today we're going to be looking at other shapes, though. We're going to be looking at shapes like this, which are half circles. So the area of a half circle, then, is pi r squared over 2. Right? We will also be looking at areas that look something like this, which have areas that are quarter circles. And those things have areas that are pi r squared over 4, because it's a fourth of a circle, 1/4 of it, right? And so we'll be finding areas of circles in that fashion today. And we'll also be looking at the shape of something kind of odd that looks like this. So you want to write this one down as well for your records. So we're going to be finding an area that looks like this. Okay? Those are weird. What should we call those? We'll call them ramps, because they kind of look like a skateboard ramp to me. A half pipe, kind of, or a quarter pipe, I guess we could say. Well, the way we're going to calculate this area is by thinking of it as, before I start writing that, let's just kind of watch what I do here. We're going to be thinking of this as a square that has had a quarter circle cut out of it. So a ramp is like a quarter circle, it's like a square that's had a quarter circle cut out of it. Okay? So what we're going to do is we're going to find the area of the square, and the square has the same base as this, so that's going to be r times r, which is r squared, right? And then for the quarter circle, we're going to subtract from it the area of the quarter circle that looks like this. Now, that circle then would have a radius of r. Okay, so the area of the ramp is equal to the area of the square I won't be lazy, I'll rewrite it. Minus the area of the quarter circle. Okay, and so here we go. The area of the ramp, which looks something like this, is equal to the area of the square, which is r squared, minus the quarter circle, which is pi r squared over 4. Okay, that's how we're going to calculate that. So you might want to have that nice little formula and probably these little pictures to go with it to remind you of where it came from. But we will be finding areas of the ramps there, and that's how you do it. You think of it as a square that's had a quarter circle cut out of it. Okay. All right. That being the case, we're ready to go ahead and jump in and begin our problems here. Now, I'm about ready to start giving you problems like this, for instance. If I call this whole function here f of x, I'm about ready to start giving you problems like this. Like, what is the integral of f of x from, -4 to 4? Well, what that means is, don't write any of this down, just watch me for a second here, because I'm just giving you an idea of where we're going with this. But what that means then basically is I need to find the area starting from 4 and ending at -4, so I need to find this area underneath of the curve in between the blue line and the x-axis. Went too far there. There we go. So I need to find that area. All right. So before we start doing that, though, what we're going to want to do is you're going to want, when you see these kinds of problems, pretty much right off the bat, you're going to want to start calculating areas using geometry right away. Okay, so first of all, start at the last point and draw a line from the point to the x-axis on both sides, like that. So we're going to stop right there. All right, so I can see that right here we have a triangle. How do we find the area of a triangle? The area of a triangle is 1/2 the base of that triangle multiplied by its height. Now the base is 2. The height is 1, 2, 3, 4. And that would be 4 as an answer. But since it's under the x-axis, we want to remember to make that a -4. So that area represented there is -4. All right? Let's do another piece. Now I want to find the area from here to here. And uh-oh, we've got a ramp, don't we? We have a ramp. How do we find the area of the ramp? Well, we talked about that on the last page. You find the area of the square, and you subtract from it the area of the quarter circle. So here's my square, and then here's the quarter circle that we're going to take away. And when we're all done with that, we will have left the area of the ramp, right? So what is the length, the base of the square? The base of the square is from here to here, so that would be 2. So 2 squared. And we're going to subtract from that the area of the quarter circle, who has the same radius as the base of the square. So that would be pi r squared over 4. So if I were to simplify this a little bit, we would have 4 minus pi. So that little ramp area there has an area of 4 minus pi. All right, so now let's continue with our little journey here. The next thing we're going to do is we're going to find the area of this semicircle up here. So let's do that. The area of a semicircle is the radius pi r squared, right? But divided in half. And the radius of this semicircle is 2. And so this is going to come out to be 2 pi when you simplify it. Underneath of that, though, we have a rectangle. And rectangles are easy to find the area of, aren't they? Base times height, so the base is 4, height is 2, so that's 8. Guess I should write these on there so I don't forget them. We'll need those in a minute. All right, then we have another rectangle over here. We have going from here to here. We have another rectangle that's 8, right? And then here to here we have a triangle. Base is 2. Height is 2. So the area is 2. And then we have one more triangle over here on the left side. What color should I do? Let's do pink. I haven't done this light pink yet. That one's also 2. It's the same as the one above it. It's just that it's a negative version of it because it's under the x-axis. So the first thing when you see problems like this, where it looks like, oh, that doesn't look like a normal function. It looks like just a whole bunch of geometry shapes on there. We'll go ahead and just do the geometry because chances are that's what they want you to do anyway. These are very common FRQ type questions. So good thing to be aware of. So anytime when you see these functions that look like just a whole bunch of basic geometry shapes put together, then chances are you're going to have to go through and find the areas anyway. Now you might not always have to find all of them, so if you kind of get smart about it, you might think, okay, well I'll only find the areas, the ones that I need, so you can start the problem ahead of time. But for me, we're just going to say, let's start by finding all the areas for today, and you can get tricky about it as you go along. All right, so let's go ahead and do a basic problem here. What is the integral? I don't want to write pink right now. What is the integral of this function from -8 to 0? Well, this basically means what's the area under the curve from -8 to 0. And so that's going to be that green triangle starting at -8. That means we're going to do here, here, and here, and then we stop at 0. So I'm only doing those parts of my graph. So the integral from -8 to 0 is all those areas starting at x equals -8 and ending at 0. And so that would be -4 plus 4 minus pi plus 2 pi plus 8. Now, if you want to simplify it, you can. I really honestly don't care too much about it. But if we simplified this, that would come out to be pi plus 8. Now, there's going to be some cases where you end up with fractions, and I'm going to say just to heck with it. Don't simplify. Just leave it alone. We don't care. The point is I don't want to know that you know what pieces we're supposed to add together. Okay? I'm going to make a slight change to this problem, though. So let me clean this up a little bit, and I'm going to add a new one. So, by the way, this is example 1, so if you didn't write it down, you might want to. I'm going to ask the same question, but I'm going to change the limits. I'm going to put a -2 here. All right. Well, that means I'm going to stop right here. Darn it, that means I got to cut my stuff in half. But that's okay. It's not a big deal. So we're going to have -4, 4 minus pi, and then we're going to take half of 8 and half of 2 pi. All right? So not a big deal, but just be aware sometimes they might stop in the middle of one of the shapes you have, but that's okay. Just take half of it or whatever portion of it that they stop at. So we have the green triangle. We have the ramp. We have half of the semicircle. The semicircle is 2 pi, but I only want half of it because they stopped in the middle. And then we also have the rectangle, but once again, I only want half of it because we stopped in the middle. And so let's see what we get out of this. Boom, 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 boom. 4 is the answer. Once again, I don't really care if you simplify it, but sometimes we can. It's not too hard. All right, so that's the basic idea there, is finding the areas and then adding them all up. So let's start pulling in some properties now. Okay, well, first of all, I don't like this constant multiplier here, but that's okay. According to property 3 from last class, we could take that 3 out. And now that we've done that, we just need to find the area under the curve from -4 to 4. So let's do that. -4 starts here, 4 stops here. So it's going to be 2 pi, 8, and 8, all put together. So in other words, 16 plus 2 pi. 8 plus 8 plus 2 pi is 16 plus 2 pi. And then we still have that 3 on the outside. And so we can go ahead and distribute that in. Once again, I really don't care too much about simplifying. I just want to see that you know how to get to the final answer. So yeah, you can still do the properties in this case. It's just that instead of starting the problem off with them telling us what the integrals equal, we had to do geometry to figure out what the integrals equal. But the property thing still applies. We're still using those properties. Let's do another one that has a property with it. Now this one might not seem too obvious to you guys, but let me tell you what property we're going to use here. It's not really typically appropriate to have the bigger number on the bottom when you're doing integrals. Okay, so what we're going to do then is we're going to start by reversing it, which I'm allowed to do so long as I put a negative in the front. And that is property 2. So remember, we don't want the bigger number on the bottom. If that happens, we want you to use property 2. So we don't want a bigger number on the bottom, so when that happens, use property 2 to reverse it. Okay? So now that I've done that, let's go ahead and find out this, which is what is the area under the curve from 0 to 8? Well, here's x equals 0, and here's x equals 8, so I need to do 8, 2, and negative 2. If I add those numbers together, the two 2's cancel each other out because they're opposite signs, and all I'm left with is the 8. So we have that, which is at negative 8, final answer. And it's negative because the limits were backwards. It would have been positive if the limits weren't backwards, because this area is above the curve, right? So why is it coming out negative? Well, it's because we were integrating backwards. When you integrate backwards, that's the outcome of that. All right, so that's another example of a property you can use. We don't want the bigger number on the bottom, and when we do have that, we want to use property 2 to flip it around, and then we can go ahead and go about business as usual. All right, so what's another property we could use? Let's say what's another property we can use? Well, first of all, for this one, we've got a minus 5 there. Okay, that's new. But I don't want a minus 5 there. All I want is an f of x. I don't want no minus 5s there. So the first thing I'm going to do is I'm going to use property 4 to split this up into 2 separate integrals. Okay, so that's property 4, splitting it up into 2 separate integrals. And now for this piece here, all I have to do is find the area under the curve from 0 to 6. So here's 0, here's 6. So if I start at 0 and go to 6, 8 plus 2 is 10. So that integral is 10. But this one here, that's a property from last class as well. That's property 6. And according to property 6, anytime you've got a little constant there, this is like the height of a rectangle, and the distance between these two numbers is the base of the rectangle. And so that's 30. And so I have 10 minus 30, which is negative 20 as a final answer. So here we saw that you can also apply properties 4 and properties 6 to rewrite it. All right. Let's do another one. I'm going to do like a granddaddy problem. So for now, let's keep it still chill one more time for one more type of problem. And then we're going to get into like a granddaddy problem, which kind of puts everything all together and really makes you think for a second here. So for this one, let's go ahead and say I'm going from, let's say negative 4 to 0 for f of x plus 2x. All right. Well, once again, we're going to go ahead and we're going to apply property 4. So let's start there. Splitting it up into 2 separate integrals. The reason I did that is because now I can find this one here because that's just the area under the curve from negative 4 to 0, which is 2 pi plus 8. Not a big deal. We got that. That's pretty straightforward. All right, what about over here, though? This is weird. Now, we saw problems like that last time, but last time I told you what the integrals equaled. For this one, I'm not telling you what the integral equals. So in this case, we need to do the old school stuff that we haven't seen for a little while. We need to do the fundamental theorem of calculus. So in other words, we're going to do this the old way that we used to do integrals, which is to integrate that. So if you integrate 2x, what does that become? It's x squared. After you integrate, you put brackets around it instead of the little squiggly here, and you put your limits over here instead, right? Then the next thing you do, enlarge your brackets here, put a minus, you're going to plug in the 0, and you're going to plug in the -4, and you're going to solve these things now. So we have 0 minus 16. And by putting all that together, we end up with 2 pi minus 8, final answer. So now compare and contrast example 6 here with example 5 that we just did. On example 5, I had a constant here, so I applied property 6. But in this case, this is not a constant. That's just a normal looking function, and since we don't know what it equals already, we have to actually calculate it using the fundamental theorem of calculus. Okay, so that was a little bit different. Now some of you guys might have thought, well, Mr. Bailey, isn't this a constant multiple? Couldn't I have put this out in the front? The answer is yes, you could have, but I just noticed that it was easier to leave it there, so when I integrate it, I just get a nice x squared instead of an x squared over 2. So I just left it in there. But there you go. So yes, fundamental theorem of calculus is an option. It's not the main highlight of these lessons, but I don't want to forget old stuff. So if you can do some integration, and if you have to do integration because they're not giving you the values up front like they did last time, then go ahead and just do the old FTC. All right, we'll do one more problem. This is a granddaddy problem. You guys ready? All right. We're going to do the integral of 6 to -4 for the following function. 5 f of x plus, let's say, 3x squared. We won't do that. I don't want to get too funky with it. It'd be too big of a number. I don't want to do that. We'll stick with 2x. And then minus 1. Before we even begin, I want you guys to notice something that shouldn't be. You guys see the thing that shouldn't be? The thing that shouldn't be is the fact that this 6 is on the bottom. That's the bigger number. We don't like that. So the first thing we're going to do is we're going to apply property 2, and we're going to switch these limits around. The next thing I'm going to do is I'm going to apply property 4 here because I don't like all these functions being put together. I miswrote something. Let me fix that. I don't want that there. All right. I don't like all these functions being put together like that. So now I'm going to apply property 6. Remember, there's a big negative in front of all this. But property 6 tells me, not 6, property 4. Property 4 tells me that I can rewrite this as 3 separate integrals. Property 3 tells me that I could take this 5 here and I can move it out to the front. Now I'm not really in the mood to rewrite all this just so I can move that 5. So I'm gonna go ahead and just get out my trusty eraser here. I'm gonna erase the 5 and I'm gonna put it up here in the front. So we have that, we have 5. Now this equals something. From -4 to 6. That's the area under the curve from -4 to 6. So that's going to be 8 plus 2 pi plus 2. So that's going to be 2 pi plus 18. Plus. We saw this one earlier. This is an FTC problem. You have to do the old fundamental theorem of calculus old school style. And then for this guy here, we see that that's a property 6 problem. It's just a constant. So we do the height multiplied by the distance between the limits for the base. Fun stuff. Whew. A lot of stuff going on here. Told you it was going to be a granddaddy problem. Got everything in it. Some of you guys might have some pretty tough grandmas, though. I guess we can call it a grandmommy problem. Okay. It was supposed to be funny, but now I just feel weird. Okay. Let's see. Okay, so I'm gonna go ahead and distribute just to, because this is looking so ugly. I do want to simplify this a little bit. It's kind of overwhelming my brain to look at all this, so I kind of want to simplify it. 5 times 18, that's 50, plus 40 is 90. Cool. And then I'm not going to do the fundamental theorem of calculus completely yet because I'm feeling too overwhelmed for that, so I'm just going to leave that one alone. But this one I'm going to simplify. That's going to be 6 plus 4 is 10, so we have minus 10 there. And I'm going to get rid of this negative. I don't like this. I'm going to distribute that in there now just to get it over with because it's in my way and it's confusing my brain. So just want to simplify all this stuff if I can. Oh, this becomes a plus now, doesn't it? There we go. Because we distributed the negative, so it becomes a plus. It was a negative, but it became a plus. Okay, so there's that. I can go ahead and also combine this negative 90 and this 10 because they're both just normal numbers. So that's negative 80. So, all right. So that's cool. Now I'm going to go ahead and do the fundamental theorem of calculus. I just wanted to put that off till the end because I was feeling overwhelmed by everything I was looking at there. So we do x squared minus x squared, where we plug in the 6 and the 4. Now 36 take away 16 is 20. And so final answer here is going to be that. A lot of work there. We did a lot of stuff to get that last one there. A lot of properties were involved. We had to do property 2 to flip the integral limits around. We had to do property 6 with the constant. We had to do property 4 to rewrite it. We had to do the fundamental theorem of calculus. We had to do property 3 to take out the constant multipliers. There is just all kinds of stuff in there. So there's that. So it's your guys' turn to do a couple problems like this. Now before you guys get started, I want you guys to stop the video and don't start 1 through 5 yet, but I want you guys to see if you can find the areas under the curve. Okay? Matter of fact, before you do that, see if you can, don't even find the areas yet, but just stop the video here and see if you could trace all the shapes that we care about. See if you could trace the shapes that we care about. When you unpause the video, I will show you the shapes that we care about. All right, so there's all the shapes that we care about. We have a little pink rectangle on the left, a blue rectangle right next to that, and a semicircle underneath of it. We've got a little green triangle, an orange triangle, followed by a brown trapezoid there, and then we have a pink ramp at the very end. Now, some of you guys might be wondering about this part right here. You might be wondering, Mr. Bailey, why did you break that up into a triangle and a trapezoid? Can't you just put those together and think of it as a triangle? You could. It's just that I've noticed that there's going to be some problems, like here, for instance, where we're going from -2 to 0, where we're going to need just that piece. And so that's why I decided to do it. But, you know, you could just do your best and then as you go make adjustments, but I think this will be the best way to break it up for this set. Now I want you guys to do another thing. I want you to pause the video and I want you to use geometry to find the area of each one of these pieces. Don't forget, when it's below the x-axis, the area is negative. When you unpause it, I'll show you the areas I got. So here's the areas I got. On the left, the bright pink rectangle has an area of -2. The blue rectangle next to that has an area of -4. The purple semicircle underneath of that has an area of -2 pi. Each of those little triangles, the green and the orange one, both have areas of 0.5, but the green one's negative because it's below the x-axis. The trapezoid has an area of 7.5, and then the ramp has an area of 16 minus 4 pi. Now, if you forgot how to find the area of a trapezoid, remember it's height over 2 times the sum of the bases. The bases are the parallel sides. So one of the bases is 1, the other one's 5, and then the height is 3. And so, no, I'm sorry, it's 4, my bad. And so we end up with 3 over 2 times 5, which is 15 over 2, which is 7.5. So that would be the area of the trapezoid. All right, anyway, all that's done. Now that we've gotten our pieces figured out, you have to know how to break it apart into geometric pieces. And now that we've calculated all their areas, hopefully you know how to do that. Now you guys are ready to begin. Now we're going to do something a little bit different. I'm going to try, I don't know if I'll be able to always do this, but I'm going to try to start doing this. Your student practice is actually going to double as your homework. So I want you guys to open up your homework now. And these problems here are the first 5 problems on your homework. So go ahead and complete these 5 exercises on your homework. And when you're all done, I will share the final answers of these with you so you can check your work. So go ahead and pause the video here and give these problems a try. And when you unpause it, I will show you the solutions. Okay, so here's your answers here. Check your work, and I will briefly verbally explain each answer to you so you can see what may or may not have went wrong. So the first 3 are pretty straightforward. In fact, the first 4 are pretty straightforward. We're just finding area under the curve. So from -2 to 0, that's the green triangle added to the orange triangle. Since they're exact opposites, the area comes out to be 0. For number 2, since we're going from -1, that's right here at the tip of the orange triangle, to 3, which is here, we're going to add the orange triangle to the trapezoid. 0.5 plus 7.5 is 8. Here we're starting at -8 and ending at -2, which means I'm just going to add the hot pink rectangle to the blue rectangle to the purple semicircle, and we end up with -6 minus 2 pi. For number 4, from 3 to 7, that's just the ramp. So from here to here, we already did that. So the ramp is 16 minus 4 pi. Now for number 5, you might not have caught this, but we do need to apply property 2 first, because the bigger limit's on the bottom and we don't like that. So we start by reversing the limits and putting a negative in the front. Then I did property 3 because I don't want that 2 inside there, so I took it out. So I have a -2 in front of this integral. Now this integral here from -8 to 7, that means basically we want to add together all of these areas because -8's here, 7's here. So we want to add everything up. So we have -2 multiplied by all the little areas added together. And I didn't simplify it because, like I said, we don't have to. The point is I just want to see that you know what to do. I'm not going to worry about your basic math skills right now. All right. So that's one type of problem, and you've gotten some of your homework done at the same time, and that's nice. So we're going to move on to a new topic here. We're going to talk about circles. It's more of the same stuff, really, but we need to review some stuff about the equations of circles. All right. The equation of a circle looks like this, where h and k represent the center of your circle. Actually, you know what? Let me see a second. So I don't want you guys to write what I'm writing right now. I want you just to watch. I will tell you to start writing in a second, though. So for now, don't write what I'm writing. I just want to share some things with you. So h and k represents the center of your circle. When you put them together, they represent the center coordinate of your circle. So if you were graphing, wherever that dot is, that would be h and k, and that's the center. The r here represents the radius of your circle. Okay, so if you were to go out, r space is this way, r space is that way, r space is up, and r space is down, and then connect those 4 dots, you've got your circle. So the r in this whole thing tells you what the radius is, the h and the k tell you the center. The x and the y represent various points that are along the circle's curve. So all those points there are different values of x's and y's. So that's the equation of a circle. Haven't seen it probably in a while, but just want to review it. But the thing is that very rarely is this problem going to be, our equations of circles going to be given to us in this form, in this class sometimes. A lot of times it's going to be given to us where the y is by itself. So in other words, let's get the y by itself. And I think at this point it would be good to go ahead and start writing with me. So the first thing I'm going to do is I'm going to minus that set in parentheses there, x minus h squared to both sides. The next thing I'm going to do is I'm going to take the square root on both sides to get rid of the square on that y minus k. Now when you take a square root, you get a plus and a minus. Finally, I'm going to add k on both sides, and this is what my final result will be once I get the y by itself. This is how the equation will usually look to us in this class. However, it's presented this way a lot of times in other classes. But for this lesson in particular, the equation is going to look like this. So I want you guys to circle this. This is the equation of a circle on the coordinate plane. I would also like you guys to add a little note here. I would like you guys to add the fact that this number here and this number here put together make up your vertex. Now I want you to notice that there's a negative here, so the h will always have an opposite sign. You want to be careful of that. Opposite sign for the h. But you don't have an opposite sign for the k. On the k, it will be the same sign. Since there's a negative in front of the h, whatever number you have is going to be the opposite when you write your coordinate. But the k will not be an opposite sign. And the reason that happened is because we added it to the other side and it got rid of the negative. But anyway, the next thing we want to look at is this piece right here. That number represents your radius. But you got to understand, whenever we're looking at these problems, they're not going to give you the radius. They're going to give you the radius squared. So they're going to have a number there, and it's going to be something like, let's say, 36. But that means the radius is 6, so you want to pay attention to that. Now, what's up with this plus and a minus? Well, whenever you get the y by itself, basically what you've done is you've taken a circle that's on the coordinate plane, and you've cut it into two halves, the top half and the bottom half. Because a function, in case you guys don't remember from pre-calculus, has to pass the vertical line test. And a circle does not. And so when you get the y by itself, you're pretending like it's a function because functions have the y's by itself. But a circle doesn't pass the vertical line test, so it's not a function. Now, if none of that's making sense, that's okay. I'm just trying to pull in some old stuff for you. But here's what I do want you to understand, is that in this process, you end up getting a plus and a minus. The plus represents the top half of your circle. The top semicircle, I should say. So that's a semicircle that looks like this. The negative one, what color should I use for that? Let's do purple. The negative here means that you're looking at the bottom semicircle. So that would look like that. Okay, so I want you guys to make sure that you know how to interpret all these parts. So the number here in green, whatever number's here, you're going to take the square root of it to find your radius. Whatever numbers are here and here, you're going to put those together to make your center of your circle. And then whether or not that square root has a positive or negative in front of it will indicate whether we're looking at a top semicircle or a bottom semicircle. All right, so that's our review for graphing semicircles. So let's go ahead and take a look at example 2 here. And this goes in your notes. So we're back to notes. We're off of homework for now. We'll go back to it in a second. All right. So for each of these problems, we're going to graph the function first on the interval indicated, in this case, 0 to 4. And then we're going to use geometry to find the value of this integral. And what this means is, since we're doing the integral, that's the area. So basically, I'm going to turn this into a picture by graphing it on this interval. And since they're asking for the integration of this, basically they're just asking me to find the area of that circle. Okay? So that's the idea there. So let's go ahead and get started. So first of all, for this first one, what is my radius? My radius is going to be this number square rooted. So my radius is 2. What's my center? My center is this number, but opposite sign. This number, same sign, put together. So my center is going to be a positive 2 and a positive 1. So I've got a circle now with a center at 2, 1 and a radius of 2. Finally, the last thing we want to look at is, are we looking at a positive square root or are we looking at a negative square root? Okay, because if it's a positive square root, that means we're going to have the top half of the circle. If it's a negative square root, we're going to be looking at the bottom half of the circle. Now for this particular problem here, I do not have a negative in front of that, so that would mean that we're dealing with this. So those are the 3 things that you need to start off with. Find your radius, find your center, determine whether you're looking at a top half circle or a bottom half circle. Okay, now we're ready to graph it, so let's do that. I'm going to start by graphing my center. My center is at 2, 1. So that would be right here. The next thing I'm going to do is I'm going to use my radius to sketch the circle. So my radius is 2 units long. So starting from the center, I'm going to go over 2 spaces to the right, 2 spaces up, and 2 spaces down. And I'm going to put 4 dots as I do that. So starting from the center, 2 spaces to the right, 2 spaces up, 2 spaces left, 2 spaces down. So that gives me a radius of 2 spaces long. And I'm going to sketch my circle. So there's my circle, but we're not done yet. And the reason for that is because I only want the top half of this circle. So I only want this. I don't care about the bottom half. So I'm going to erase that. There we go. We have now officially graphed it. So step 1. Step one is to find your radius, center, and half. Step 2 is to graph that. Start off by graphing your center, then graph your radius, and then graph the half that you care about. Step 3 is, now I've got everything in place that I need to find this integral. What this integral is asking me to do is it's asking me to find the area under the curve from 0 to 4. So from x equals 0 to x equals 4, I want to find the area under the curve. So that's this whole thing. Now as you can see, we've got 2 shapes there between the curve and the x-axis. I've got a semicircle, and since it was lifted up high, there's also a little rectangle underneath of it. And so this will be the area of the semicircle added to the area of the rectangle to give me my final answer. So the semicircle has a radius of 2. It's a semicircle, so it's going to be pi r squared divided in half. The area of the rectangle is 4 times 1, which is 4. And so we actually end up having 2 pi plus 4 is my final answer to this integration. So step 1, identify your parts. Step 2, graph it. Step 3, calculate the area, because that's what the integral is asking for. All right, let's do another one. Step 1. I would encourage you to pause the video here and see if you can find all the parts. What's the radius? What's the center? And is this a top half or a bottom half? The radius would be the square root of this number, which is 9. The center is going to be the opposite of this number combined with this number. And so that's going to be -1, 4. And since there's a negative in the front of it, we are looking at a bottom half circle. Okay, see if you guys can graph that. Pause the video and see if you can graph it. When you unpause it, I'll show you the graph. Okay, so my center is where we'll graph first. So left 1 up 4 is right here. I've got a radius of 3. So right 3, left 3, up 3, down 3. And now I only want the bottom half. So my circle is going to look like that. All right, good enough. Now we're ready to find the area. That was a little bit tricky. See if you guys can do this. How would you find the area of that shape? There's more than one way to do it. One way is to think of it as 2 ramps and 2 rectangles. That's one way to do it. And that's probably the way it makes more sense. There's another way that's a little bit faster, and if you can think of it, go for it. But I see here 2 rectangles, one here and one here, and I see 2 ramps. So that's the approach I'm going to use. But if you want to see if you can find a different way, because there is another way that's a little bit faster, you can give it a shot. All right? But let's go ahead and figure that out now. So the rectangles each have an area of 4. The ramps each have an area of, let's see, 16 minus 4 pi, and there's 2 of them. And then if we just go ahead and put all this together, which you don't really have to, 32 plus 8 is 40, minus 8 pi would be the final answer. So there you go. All right, let's move on to number 3. Okay, so I made a slight change just now. I changed this to a 0. So look at your notes and make a correction there. I want to change that to a 0. Okay, so once again, let's see if you guys can go ahead and find your parts here. So step 1, find your center, find your radius, and then determine whether it's a top half or a bottom half. When you unpause the video, I'll show you what I got. All right, so the radius is the square root of 25, which is 5. The center is tricky. The center is supposed to be the number that's being subtracted from x, but there isn't one there. And it's supposed to be the number that's added outside the square root, but there's nothing there either. In that case, that means the center is 0, 0. So if you're missing either the h or the k, then that means they are 0. Next, is this a top half or a bottom half? Well, I have no negative in the front there, so it must be a positive. So that means it would look like a top half. All right, number 2, let's graph it. Radius is 5. And it's a top half, so I'm only going to do the top half of that circle. And there's that. Now, step 3, I want you guys to pay attention to something. I'm only going from -5 to 0. So I'm only going from here to here. So in other words, even though I'm graphing the top half of a circle, I only want the area of the left quarter circle. So you do need to also pay attention to the intervals that they're asking about. And so it's a quarter circle. So this area would be pi r squared divided by 4 because it's a quarter circle. And so this final answer here will be 25 pi over 4. Okay, so there you guys have it. Once again, the student practice that precedes after this is going to be your homework. So notice I've numbered it 8, 9, and 10. So you're actually going to jump up to part B on your homework right now. You're going to skip a few problems, and you're going to do numbers 8, 9, and 10. So go ahead and do numbers 8, 9, and 10. And unpause the video. When you're all done, you will see the solutions to these problems. All right, so I've color-coded each one. The answers are boxed there on the right side. If you didn't get it, I'll verbally go through the solutions here with you now. So for the first one, here's your radius and your center and whether it's a top or bottom half. Here's the graph. It's a semicircle that's dropped one space down, and as a result, you have a little rectangle between the semicircle and the x-axis there. So the area is the area of the rectangle added to the area of the circle. The area of the rectangle is 1, and the area of the semicircle is pi, but they're underneath the x-axis, so they're both negative. So the final answer there would be -1 minus pi. For the next one, the radius is 4, the center is 3 and 0, and it's a top half circle. And when you graph it, it looks like the green graph that I've got there, but notice that I'm going only from 3 to 7. And since I'm going from 3 to 7, that's actually only the purple part that I've highlighted there in the green graph, which is a quarter circle. So the area of a quarter circle is pi r squared divided by 4, which will give us an area of 4 pi. For the last integral, we have a radius of 6 and a center of 0, 0 with a top half circle, so it looks like the graph I've given here. And since we're going from -6 to +6, it's the entire semicircle. And so the way you find the area of a semicircle is pi r squared over 2, which gives me 18 pi. So there's your answer there. So we've got 3 more problems from our homework done. And then there's some more practice problems for you guys to do on your homework. But that should pretty much do it for our lesson today. And so the rest of the homework problems are for you guys to do. And we'll see you guys in class. Have a good one.